Hello everyone, my name is Rishabh Pandey. Today I am going to talk about sorting algorithms, in particular parallel sorting algorithms run on a multiprocessor. Sorting, as you might know, is one of the most studied problems in computer science, not just because of its theoretical interest, but also because of its practical importance in the computer science industry. Sorting in computer terminology is often defined as the process of rearranging a sequence of values in ascending or descending order. Now, we'll talk about the content of this presentation and see what we'll go through. And so, here is a brief overview of all the content we are going to cover today. We'll start with the basics of sorting, why sorting is fundamental to computer science and why its importance cannot be ignored in the field of computer science. We'll talk about certain sorting algorithms, look at their best case, average case, and worst case time complexities. For example, insertion sort, which has a best case time complexity of big O of n, seems to perform better than merge sort, but when it comes to average case and worst case, its time complexity is drastically reduced, leading up to big O of n square, while merge sort and quick sort perform better in this case, merge sort being big O of n log n and quick sort also giving a big O of n log n for average sort. But these are sequential sort algorithms. We will talk about parallelizing them and let's see how we can achieve more speedups. We'll briefly talk about analyzing parallel algorithms. We'll talk about two parallel algorithm key metrics performance indicators, which are work and span. After that, I'll start with the merge sort and find a way to parallelize merge sort. Then we will talk about quick sort and a way to parallelize quick sort. Finally, we will do a comprehensive analysis of parallel merge sort and parallel quick sort. Along with it, we will also compare it with another algorithm which will be a mixture of merge and quick sort, known as parallel merge quick sort. Towards the end, we will start with the discussion of challenges which will be faced while doing this work and future work, which is an exciting area of interest to those of you who want to explore sorting as a subject. In the end, I will give a reference of all the material which have been used to explore this study for future work for you guys. Thank you. Okay, let's start with the basics. Sorting. It is fundamental to computer science because of its practical importance, which cannot simply be ignored. It is important for searching algorithms, load balancing algorithms, and many more use cases. One such use case is use of sorting for computer programs such as compilers and editors, which often choose to sort tables and lists of symbols stored in memory in order to enhance the speed and simplicity of algorithms used to access them. Because of both their practical importance and theoretical interest, algorithms for sorting values have been the focus of extensive research into both academia and industry, and which is also one of the reasons why we chose this topic. Here in the table is a list of commonly known sorting algorithms, as you can see, such as insertion sort, selection sort, bubble sort, merge and quick sort, with their running times in best case, average case, and worst case. Here n is the number of elements which needs to be sorted, as you might already be aware of. Now, throughout the semester, we have talked about parallelizing and parallel processing, how parallelizing can help us achieve speed up we intend to have for execution of our program. And the same is true in field of sorting. With the advent of parallel processing, parallel sorting has become an important area of algorithmic research. The literature review for this study extensively included use of research papers, academic journals, and books from published authors. Now, before we talk about our first parallel algorithm, let's talk about some basics of analyzing parallel programs. Two key measures of runtime are work and span. Work can be defined as the amount of time it would take to run the program on one processor, often denoted as T1. Span, denoted as T infinity, is the amount of time it would take if we have infinitely many processors. This is what we call the hypothetical ideal for parallelization. Now that we know what work and span for any algorithm are, we can bound the parallel speedup we can get for any algorithm. So let's say you have P processor. The maximum possible speedup would be T1 over Tp, where Tp would be the running time on P processor. Estimating this value Tp helps us to identify the level of parallelism that can be achieved. The fork-join framework achieves an asymptotic bound on Tp in the order of T infinity plus T1 by P. This is big O notation. The fork-join framework is an implementation of executor service in Java that helps you take advantage of multiple processors. The framework was designed to simplify parallelism for recursive tasks by breaking the single task into independently many until they are small enough to be executed asynchronously. This is the reason in particular we chose divide and conquer algorithm such as merge sort and quicksort. We have used the same framework in our simulations and tests to attain high speedups. Most programs have parts that parallelize well and parts that don't parallelize at all, and the latter becomes bottleneck when we talk of parallelizing programs. This is directly related to the Amdahl's law that we discussed in the class. And remember, when we talked about minimizing sequential portions of the program, this is what we will be aiming to do in our sorting algorithms. Now let's start with the first algorithm. Merge sort is based on the divide and conquer approach. It follows this approach by splitting the sequence into multiple subsequences, sorting them, and then merging them into the sorted sequence, which gives us our final result of a sorted array or sorted elements. As you can see in this animation, it is a recursive sorting procedure that is employed to sort the elements. To sort an array of n elements, for example, we perform the following steps in sequence. If n is less than 2, the array is already sorted. As you can see, 1 over here is already sorted. 3 individually is already sorted. Otherwise, if the value of n is greater than 1, we perform the following 3 steps in sequence. We sort the left half of the array using merge sort the right half of the array using merge sort, which is our algorithm, and then merge the sorted left and right halves. This divide and conquer algorithm gives an overall time complexity of O n log n, as you have already seen in the previous slides. Now we will talk about parallelizing this merge sort. So let's learn about parallel merge sort. In parallel merge sort, input elements are divided into two equal parts, and each part is processed by a separate processor, and each division is mapped to a new processor until every processor has its own data to be sorted. This division forms a tree-like structure which can be implemented as a hypercube as well, but that is beyond the scope of our discussion today. However, those of you interested in exploring further the topic can check out the references section towards the end of this presentation. So, after division, all processors will perform a sequential merge sort to sort their own N over P data locally, where P is the number of processors and N is the number of items. To gather the results, each processor will merge its own result with its parent in a bottom-up manner. Now, let's look at another interesting algorithm, quicksort. Quicksort is another divide and conquer algorithm which was developed by Tony Hare and have been around for more than 6 decades now, but still very popular for sorting large sets of data elements. It is a sorting in-place algorithm that recursively calls itself to sort the items in an array. The algorithm calls itself n number of times with input length dependent on the partition procedure, about which we will talk later. As you can see in the animation on the slide, sequential quicksort algorithm is a recursive procedure which works as follows. It selects one of the items as a pivot, divides the list into two sublists, a lower list containing numbers smaller than the pivot and an upper list containing numbers larger than or equal to the pivot. The lower list and the upper list is recursively then called to sort themselves. The final sorted result is a concatenation of the sorted lower list, the pivot, and the sorted upper list. Obviously, the main operations are done in partition procedure here. Firstly, it chooses a pivot value to sort the elements into two sublists, upper and lower. All the items in the former list are greater than or equal to the pivot value. The later list contains the items that are less than the pivot. Then the quicksort algorithm is recursively called on each sublist. The same process is repeated to each sublist until partitioning cannot be performed further. Finally, each list will contain a sorted part of the original list. Sequential quicksort has a better runtime complexity compared with other sorting algorithms such as selection sort, insertion sort, and bubble sort, as we have already seen in the presentation earlier. Merge and heap sort algorithms, however, have the same growth rate as in the quicksort, except for the worst case running time. However, worst case is rarely to occur, and so we will work under the assumption and see the parallel version for the quicksort now. Parallel quicksort algorithm can be implemented in different ways, but for our experiments, we use the main idea to do the partitioning on the original list using a single processor and then assign the upper sublist to another processor for further processing. As you can see in the table, these are the steps we followed. At step 1, we do the partitioning on the assigned original list and go to step 2. We check if any processor is available. If yes, go to step 3, which is assign the upper sublist to the processor if its size is greater than 1 and mark processor as a child. But if there is no more processor available at step 2, we directly go to step 4, that is, we perform quicksort on the assigned list and go to step 5, send the results to the parent processor and then go to step 6. So this way we keep on repeating and using the different processors available for us to sort the list. Now let's look at another algorithm which is a combination of both algorithms which we have learned till now, parallel merge sort and parallel quicksort. Parallel merge quicksort. This algorithm is a combination of merge sort and quicksort. It uses parallel merge sort to divide the data among processors and then use quicksort to sort the data locally at each processor. The parallel analysis for this algorithm is the same as parallel merge sort, since in the best case, sequential quicksort has the same complexity as the one for sequential merge sort. Results show that parallel quicksort has better running time for both large and small data size. In terms of parallel efficiency though, quicksort algorithm is more efficient to be applied on a large number of processors, that is 8 or more processors, and thus we decided to focus on the parallel quicksort and parallel merge sort for our analysis, which is shown on the next slide now. Analysis of quicksort and merge sort. Now that we have discussed the parallel algorithms, Let's discuss the results and evaluate them in terms of running time, speed up, and parallel efficiency performance metrics. However, before we do that, it is crucial to note that hardware plays an important role into the level of parallelism you can achieve, and so the hardware and software specifications along with the used implementation parameters are shown in the table here. As you can see, we have used an Intel Core i7 machine with 8 core processors and 16 logical processors. It has a 16 GB RAM. For software we used Linux Ubuntu 21.04 and run our simulation using Java version 18 on a Java compiler. The algorithms are evaluated according to different input sizes and different number of processors for different runs. An average of multiple runs is considered to record the results. Now let's see this in a graph form. Now let's talk in detail about the key metrics on which we based our results. Runtime evaluation, speed up evaluation, parallel efficiency evaluation. Let's start with runtime evaluation. The general behavior is the same for the two algorithms. That is, as the number of processors increase, the runtime is reduced due to better parallelism, better load distribution among more processors. This is the case when we move from 2 to 8 or 16 processors. However, we noticed as the number of processors increased beyond a certain threshold for a dataset size, the runtime also increases. This is because as the number of processors increase on a specific dataset size, the communication overhead increases too. Consequently, the benefits of parallelism are decreased. This is the reason why we did not opt to go for a more powerful machine with more number of processors, because 16 processors were sufficient and more than 16 processors started showing the result of decreasing runtime. The second key metric on which we discussed or based our results are speed up evaluation. The speed up is the ratio between the sequential time and parallel time. The results show that parallel quicksort achieves the best speedups, which values up to 10, especially on large number of processors. The third key metric is parallel efficiency evaluation, which is the ratio between speedup and the number of processors. The parallel efficiency algorithm for each algorithm, including merge quicksort, which we discussed earlier, have different results. The results were calculated corresponding to different dataset size, and we could find that on small number of processors, parallel merge sort achieves up to 96% efficiency and was the clear winner, followed by merge quicksort, which achieved up to 93% parallel efficiency, while quicksort only manages up to 72% efficiency. However, with increasing number of processors, the picture is entirely different. Parallel quicksort achieves the best efficiency on large number of processors, that is 8 or 16 processors, compared to other algorithms. Parallel quicksort managed to achieve 88% efficiency with 8 processors, while merge and merge quicksort achieved only 52 and 49% efficiency. This is because quicksort has better speed up values when applied to 8 or more processors. Challenges in future work. Let's begin with the challenges. The first challenge one might issue while dealing with parallel sorting is load balancing issue. Let's say even if there is enough parallelizable CPU available work to make parallelism worthwhile, we need to ensure that the work is evenly distributed among different processors on the machine, which in itself is not an easy task. This is complicated by the fact that different chunks of work may differ widely in the time required to execute them. Some elements may already be sorted, while others might require a lot of sorting. Also, we often don't know how much work Each chunk will require until we execute it till its completion. The second issue is performance of parallel algorithm depends on the underlying architecture or the hardware. Communication overheads also increase with an increase in number of processors, which complicates the problem and reduces the parallelism. Now talking about the future work, we can talk about and explore superlinearity in parallel merge sort, a reference to which is provided in the reference section next. It's an exciting area and I am willing to participate and engage in someone wanting to work in the field. And finally, here are the references which have been used in this work. I have included all the references which I have used, and viewers are encouraged to further explore the topic and read more from these sources because sorting will continue to be an exciting and yet important area of interest in the field of computer science. You can explore topics like hypercubes and superlinear algorithms for quick sorting. Thank you very much.